Well, thank you for inviting me. I am back in Coldelco less than a year. I was there before 1998 until 2005. And well, it took me a while to find some information. I knew things were done, had been done, and as in many places we run surveys and then they stay there and there's not much interpretation or study for that except a few holes and that's it, and move to the next one. So it's a good opportunity for me to look at the information we have, and I basically collected most I can, and we will have a lot of work to do.
You got to hit the first arrow
Here, yeah,
in the
sometime.
middle, and then
There we go. Awesome.
Sorry,
longer.
Okay. You good?
so okay, this is
There.
well. I found information about 3 important deposits. You know Chuquicamata district, and well, north of Chuquicamata district is Radomiro Tomic, and south of it, these Ministro-Hales. They were not very hard to find. It's such a big deposit. And then close to El Salvador is another area that, well, I just saw the information that they were looking for some extra copper for the mine. It's running out of copper. And as you can see, well, this is Chile. This is north of Chile. There's nothing, no cactus, no nothing. So basically copper. And these are this is Chuqui mine, Chuquicamata. And up here is Radomiro Tomic. And down here, MM or M8. This is along the big West Fault, very well known for the occurrence of these giant deposits. So what I could find was around Chuqui on 2005 and then 2010. There were some IP surveys, and actually it is maybe this one. It's the first time that Coldelco runs IP survey seriously somewhere. I think it's because the copper was, the mine was, the rocks were superficial and the alteration was easy to find. At these days, it's harder. This area was well known, but was like a test for knowing the IP response. It was done by a MIMDAS survey. And well, the other reason Coldelco didn't use much IP, it's because it didn't work much with the caliche. Very insulating cover. So very hard to inject current. But these new systems can go deeper and with less signal. So this is the image for this year. And here you have Chuqui. Here you have the pit for Radomiro Tomic, and here you have a small pit for M8. But back then, here, it was just a small starting pit. And now the lines are covering something that is being mined already. These are the lines during that year, and this is the pit starting. This is now. All this area is it's a well-known oxide and then secondary enrichment. Porphyry. But it was very interesting to know we could get that line before the pit. And not much data, not much, should have been better to do more, but it was the first time. And well, here's the geology, the big fault. You have one deposit to the right of the fault, the other one, Chucky is in the middle, and MM is to the left, to the west side. Well, we have many intrusives that has been intruded by these late porphyries, and they are around 33 million years old. So this line we had this interesting IP anomaly, and as Ken said, there are some conductors, but I haven't seen yet what's really going on. There's a lot of information, a lot of drill holes, so now I should go back and see what are these things. I think I've seen that also in another small porphyries. It's probably pyrite, could be more massive. Not sure. Well, this is close to secondary enrichment. This is more likely to be the oxides. But still some conductors. I'm not sure what are they. These are just some geological sections I got, and it's a general model, but not exactly the section for the IP, but it goes through, this is the oxide. Upper oxide layer. Then we have another lower oxide. This should be resistive and also no IP response. And then we have these are basically the secondary enrichment, which really gives us a good IP anomaly. It's not very hard to find IP anomalies here now. This is a north-south section. This is RT. This is Chucky. So it has been mined up. This was for 2012. And here is copper oxide. This is secondary enrichment. And this is more primary sulfides. And all of them gives IP response, and probably the conductors are secondary. I'm not sure if secondary enrichment, but probably more, that's a good question actually. Could be fractured zones, more wet zones, and since we have so many drill holes around here, it would be good now to go back and check what are those rocks and start doing also, trying to do borehole geophysics and get a better understanding why we're able to. This is another line, and same type of response. Well, this is not very well inverted, but probably there is some artifact here. But again, strange conductor, but I'm not sure what it is. And IP response, probably because of the depth, it's the secondary enrichment, which is not very, it's still disseminated. You know, there is a mix of oxides, maybe with the groundwater or something going on here, fractured, not sure. And then, well, this is a more new model, the same things that Richard was showing, this modeling. You have all these intrusives, and these are the primary sulfides. These are more secondary enrichment. So basically the IP anomaly is stronger around here, these blocks here and there. And well, perhaps because of the resolution of the survey, we just see a general anomaly and not many details. In the future, well, this same thing, but with a big block in the secondary enrichment, but not such a big anomaly here. Again, we should go back and see what happened, why we have such a big chargeability here but not there. Or, yeah, I think the geological model is right. Or maybe the data, we have to go back and look at the data. But it's not that simple, no? But at least you see chargeability anomalies in porphyry covers. And this is a slide showing some, in the scale you see this is a very small grain. So you have the chalcopyrite, chalcocine pyrite. So the chalcopyrite and pyrite are small grains and kind of disseminated, no? And the chalcocite is replacing the chalcopyrite. So that's basically the mineralization in this porphyry.
Would that be in the transition? They said it was a mix, so one of the categories was a combination supergene.
Yep, I didn't see any in this publication that example, but I can get something later and see the oxides with the sulfides.
So maybe Dick, is it the chalcocite coating the pyrite grain?
Yeah, I mean, that's transitional ore, you know, in the sense.
Oh.
Chalcocite will replace the copper iron sulfides first, so that looks like that's right at the boundary of hypogene and supergene. I guess you have a transitional ore or weak supergene. I can't remember.
It was a mixed one thing, yeah.
Yeah, so photosecondary, maybe a weak secondary sulfides, yeah, right at the
Mixed.
transition.
There, one
Yeah,
pattern.
pale blue.
Yep.
So with time, would eventually the chalcocite be the dominant one as
Yes.
opposed? Okay. This is stopped then.
Pardon me?
The weathering process stopped. That's what
No.
this. Oh.
They'll take the pyrite next.
Then we have a survey. Well, that was a very simple IP survey. And then 8 years ago, they did this another one around this another porphyry that is not as important and as good as this one, but still, we're looking for resources everywhere. And same thing. The results for this line, you have the resistivity model, the conductive. That was the plan for the pit area, so it was possible to measure back then, before the pit. And we see these conductors but I'm wondering what are they actually. But the interesting thing is very strong. Well, it's strong. 30 millivolts per volt anomaly just underneath, and something else to the west that I'm not sure if they are planning. They have planned mining there. These things are happens a lot that we run surveys and then somebody's gone and the data stays there and nobody really uses it. So it would be good if I am able to contact them and see what are they doing with it, if they are doing something or not.
Do you think that's the fault zone coming through the middle of the MT and resistivity?
Yeah, probably it is. Probably it is. But,
Is that the fire rusted?
That's what I'm,
yes.
yeah.
Yeah, I'm wondering why is this, what is lithological response to this type of rock? But clearly, yeah, that's the fault and those are the intrusives. And this should be, actually this image, this section has been modeled, and you can see in the depth, you can see a very, very strong resistor, which would be the big intrusive underneath these big deposits. Same that was shown by someone here.
We can show a lot of conductors, big
Yep.
conductors in the MT under deposits.
The last one.
Resolution? No?
There was a Z10 that showed a big resistor.
Oh, that was at Lone Star remark.
Yeah.
Lone Star.
Lone Star, all right.
Yeah, Lone Star. Yeah, that's a big resistor underneath. Same thing you can see here in another reprocessed line. And, well, that's one line. That's information is already, well, the pit is already has been started. So, on the other line, that is a little bit norther, shows another anomaly going to the west. Same one probably going that way. Again, the fault and the resistor underneath. Probably this is type of rock that is in that area. Conductor. I don't think it's, well, maybe there is some relay.
Could it be a valley fill or something? I mean,
Could be.
I mean,
Or the type of rock, I'm not sure, but this is very conductive.
yeah, but I mean, a volcanic, unless it's got saline water or something, it would seem to be.
Big volcanic.
Mm,
I have to study more about this. It's a,
yeah.
well, I was just grabbing this information. Took me a while to find the geophysics and to ask for the geology and then try to put something together.
How do you explain the chargeability of the last diagram there on the left-hand side?
Excuse me, I don't understand.
Can you?
You have a chargeability anomaly. Right?
Yes.
Yeah. But that's the most interesting thing in this diagram. The conductors on the right-hand side are just faults, shear zone. So you have an intrusive, you have like a stalk, it's a small porphyry.
Yeah. Well,
So probably intruded along a shear zone. And so you have high resistivity in MT, high resistivity in DC resistivity, and high chargeability.
yeah.
It has nothing to do with supergene enrichment. It's actually something like French.
Supergene enrichment, you mean that?
It's not. Well, the main anomaly I see in this diagram is in the chargeability.
Yes, usually.
It's more important,
Yeah.
and it has nothing to do with weapon at all.
No. Chargeability is usually the big intrusive with disseminated sulfides.
Probably disseminated, yeah.
Yeah. So this is the technique, the best technique for porphyries, and works very well in Chile. You have supposed to have resistives, chargeabilities, and well, also the resistive underneath showing the big intrusive. we have to be careful with these chargeability anomalies sometimes, because when you model a very resistive, when you have a very strong resistor, somehow in the inversion process makes the chargeability be stronger than it is. So, but at least there is an anomaly. Usually we see a very, very very
you actually measure this in the field.
yes.
So you have the indicator of the area that is shown, the curve, and you get a number. So if you show the pseudo section of your measured chargeability, you
Oh,
find
yes.
that it looks like that.
Yes,
So when you then model it, you're going to fit your model
Yeah.
to satisfy your observed
Right.
chargeability and observed appearance.
right.
So providing that your measurements were done correctly, you should really be able to explain why you have your chargeability
Yes.
very high within your resistive stock.
Yes. Still will be a good IP anomaly, IP data, but just be careful when you find a very, very strong chargeability for two reasons. Because it could be a very resistive, but makes that in the inversion makes it look stronger. And the other thing is, many times you have a lot of pyrite, and happens a lot. No, so sometimes you have to drill. You drill here and you realize what is it. If it is pyrite, probably the copper could be around in another not very high anomaly next to the strong anomaly. Well, you know the Salvador mine is another important porphyry deposit. And this was much later. This was done on 2012. And this time it was a 3D Linda survey. It was also taking the magnetotelluric information, but the mine was very noisy. So the data is okay, but they didn't model the magnetotellurics. But still, well, this is a prospective area around the mine, which is open pit and underground. So looking for more resources. Now I got some geology. Excuse me, it's not very, very beautiful sections, but what I got is this is the geology, and I think these are just these 4 lines. It was not possible to run that one, and we can see the results. These are two 2D sections. This is line probably 1, 2, 3. This one. And again, you have a nice resistor. And well, we would expect chargeability maybe around here, but it's not. It's on the sides. Again, I was asking for drill hole information. Took me like a week to get something, but the holes I got are wrong, are not in this area. So I wanted to calibrate the anomalies with the drill holes. And it's amazing, but people working here, sometimes they didn't know that we ran this survey. So there's a lot of work to do. Looks like we are running too much. And plus, there are maybe 200 geologists in Coldelco and 1 geophysicist. Yeah. So, well, it was a good motivation that you asked me to put something together. I didn't really spend much time, but it was good to be able to put something together, and now I can do more work and perhaps publish something in the future. Well, these are Coldelco's deposits, so nothing wrong to publish it, no secrets.
So, I've been to Cerro Colado many years ago.
Yeah.
And so Cerro Colado was a little intrusive stock sitting in a sea of andesite. Okay. So again, the blue bit could be the stock, that's the middle.
Mm-hmm.
And then you got that, what goes to lower resistivity is you're actually going out and you're getting a contrast between the two original rock types with an overprint of hydrothermal alteration.
Could be structures there.
Pardon me?
Could be some structure,
Could be, I mean, yeah.
and then you have
That whole row is along an old Paleocene fault as you go out from Vergesa all the way out. So.
well, with the 3D modeling, it's much better to get details. And in this case, we have this is the geology with detailed information gotten by the drill holes. So I got that section. Fortunately, the geophysics is oriented that way, but since we have a 3D model, there is a cube that if I had the data, I can, and the software, I hope I will, I can cut through this section and see details for the responses. I'm not sure if I will get exactly what I hope to, but these are secondary enrichment. And same thing again, mixed mineralization and oxides on top, some. Same thing for north-south section. Well, this is cut at some depth, that level. So you can see, maybe we cut this, that level. You don't see this. That secondary enrichment would correspond to that area. So what I would hope is to see these things, especially these things in the IP, and we could see that. This is the 3 model. I think we should do much more 3 modeling, 3D surveys these days. It's not much more expensive, and after all the work, going to the field and getting the paperwork for safety and all that, it's better to get as much information as you can. So we can cut this. I have to get this model again, cut through it, this side, and then layers going deeper, and should be able to see these nice details. What are they? That's, again, you see resistors and some conductors. And the chargeability in these blobs that could be those secondary enrichment. And I made if we cut the 3D model through that line, we should see these blobs here. And here, well, this is for that area, that's the conductor and IP response. Probably small things isolated like that. And probably those are oxides. But still, I have to put the drill hole information, which is really a lot and really good. And this is a 3D model, should give us much more detail and much more answers to what we think are the IP and resistive anomalies. Plus, would be nice to have a borehole geophysics. Maybe, I'm not sure about borehole IP, but to see in situ the anomalies are much more different than the rock samples. So we will be able to, well, to make sure that it's an IP response, that's always a ground survey, but if we get more information about the conductors, we could run run airborne electromagnetics, which is easier, and maybe find more ore body deposits. So, well, I have some homework to do, and well, that's it.
Thank you very much.